Okay, so let's talk a bit about dictionaries. So any running Python program at any time has many active dictionaries, even if the program that the user is executing doesn't explicitly use a dictionary. And some of the examples are the ones that we saw in the pool. Module namespacing or key arguments. And this quote, I took it from Fluent Python book, which is very nice, and I recommend you to watch it. So it has three parts. So one is hashing and dictionaries, which is basically hashing is the backbone, the engine behind dictionaries. A bit on dictionary security, how secure are our dictionaries, and a bit on some performance optimizations. Dictionaries, because they are everywhere, they are highly optimized. And I think one of the things I would like you to get out of these talks is that Python core developers have a level of detail on the craftsmanship that they do that is amazing. So let's get into the first bit, talking a bit more about hashing and dictionaries. So let's start at the beginning. And sorry if this is something you already know, I just don't want to lose anyone. So what is hashing? So a hashing function is something that can be used to map data of an arbitrary size to an integer. And the things that a hash function must satisfy by definition is that if two objects are equal, then their hashes must be equal. But if you're going to be using this everywhere, you're not only going to ask the minimum of the definition, you also want a bit of extra. And we'll talk about in a sec. So one of the things that make hash tables, hash functions so nice is that we use them to build hash tables. And hash tables are one of the most beloved data structures in computer science. You probably run into them all the time. You probably have been asked about them at interviews, and at your daily job you use them. And one of the nice things is that on average, most of the operations you want to do, like insertions, search, deletions, are all constant time. And this is kind of from a picture I took from Wikipedia, how a hash function can be drawn. You have some keys, and you use your hash function to map it to certain buckets. And we will talk something that I mentioned now because it will come back later, is that we talk of a collision when you have two of these things, like for example, John and Lisa, and your hash functions map them to the same bucket. And in that case, you will have a collision. So we talk about asking for more than the minimum of a hash function. And one of the things that we want to ask is that it will minimize the collisions. So we want to minimize this situation where we have two different keys and we map them to the same bucket, because that needs to be resolved. And no matter how we resolve, it will degrade performance of your hash table. So that is something you want to minimize. And you also want it, the hash function, to be something that is cheap to compute, because you're going to be computing it quite often. Now, why am I talking about this? Why am I talking about tables and hash functions? I'm talking about this because Python dictionaries are implemented using hash table. They also Python sets. So that is why you have these kinds of errors when you're trying to use, for example, a dictionary as a key to another dictionary, which was one of the questions of the poll. You will get something like this: type error and hashable type. In this case, is list, but you will get unhashable type dict if you try to use a dict. And this has to do with the fact that it's not a valid input for your hash table, for your hash function. Let's talk a bit more about this. So this is the formal definition of what it means to be hashable in the Python world. An object is hashable. Let's read together. An object is hashable. It has a hash value which never changes during its lifetime and that can be compared to other objects. Hashable objects which compare equal must have the same hash value. Hashability makes an object usable as a dictionary key or set member. So basically, what was missing was the hashability. And if we digest this definition a bit more, it has a hash value means that it needs to have a dunder hash method defined, and that which never changes during the lifetime. It is talking about mutability. It doesn't depend on mutable attributes. And can be compared to other objects is talking about having a dunder ek method. Okay, so we have like different pieces of our puzzle, and we have a definition that kind of puts it all together. So we are talking about unhashability, we are talking about mutable attributes, we are talking about comparing things. So let's digest this a little bit more. So user define objects hashable. So if I define an object, and is that going to be hashable? And by default, yes. The dunder ek method that is used is the identity. So two things compare equal only if they are the same object. But you can override all these behaviors. So we said for something to be hashable, you have to have a dunder ek method and a dunder hash method. Well, I mean, you can override these things and tune and customize the behavior you get. So these two over here are kind of common pitfalls, because, well, this is actually how you have to do it. So if you don't want hashability, you do this. This is the way to go. You set dunder hash to none, and now your objects don't have hashability, because maybe that's what you want. But this is a common pitfall. So if you override one of these functions, imagine you override dunder ek, but you don't override dunder hash, then you lose automatically the hashability of your objects, because Python behind the scenes will do this. So that is a bit of a precaution. But now let's talk about the case you probably want, which is to override these two things, but keep the hashability. So usually, I'm going to take out the point. So usually, if you decide to override these things, you have to go back to the definition and remember that you need to build it based on things that never change during their lifetime. And here we have a bit of a simple example. So you can use the built-in hash function. You don't need to become a cryptography, lucky for all of us. So what you usually do is you get a tuple of your immutable attributes and you pass it to hash, and that is how you tune your hash dunder hash function. So this is a bit of an example. So let's slow down on this example. This is a class person, and it will have a name, which will be an immutable attribute. And I'm defining my dunder hash as the hash. This is the built-in function hash. And I'm passing a tuple. Oh, sorry. It's a bit annoying that you cannot click with the pointer. And I'm passing a tuple of one immutable attribute. And this is how you usually do it. You could have more than one here, like you could have an n tuple, that's fine. But this is how you usually would override your dunder hash, with some tuple passing to the built-in hash. And then you also are overriding your dunder ek. And this is quite a simplification, because I'm saying that two persons are the same person if they have the same name, basically, if they. So this is like a very simple example, but this is kind of how you can do it. So like to redefine your dunder hash, you usually call the built-in hash with some unmutable attributes. And your then derived, you can redefine it however you like, but remember to redefine both. So that was a bit of a walkthrough on the kind of foundations of dictionaries, and kind of answering a bit about what values can you use as key of a dictionary, as values of a dictionary, and so on. Now let's talk a bit about dictionary and security. And there has been quite an interesting evolution, I would say. So if dictionaries are going to be everywhere, you kind of are interested in trying to make them robust and secure to attacks. So imagine, for example, that you have an HTTP server with a get query string. Let me get the pointer again. So this gets parsed into a dictionary where these things that I mark on, how do you say, on bold letters are the keys of the dictionaries, and these will be the values. So this gets parsed into a dictionary. So what is the danger of this? Basically, if your attacker gets hold of knowing what your hash function is, they can fabricate keys that are designed to collide. And then they would degrade the performance of your service for legitimate users, which is called a DOS attack, a denial of service attack. Other examples of things that get parsed into a dictionary and could put you in the same situation is parsing a JSON also produces a dictionary. Uploading a CSV file also gets parsed into a dictionary. And in general, in any other situation you can think of where you don't have control of what the keys are or how many of them are, you can get put into this situation. So let's talk a bit of an evolution of Python dictionaries. And there have been 3 versions of security on Python dictionaries. The first one was a non-cryptographic hash algorithm. It was efficient, but it was prone to this kind of attacks that we just described. And this would, it was proven with an example that attackers could exploit the worst case of dictionaries. So this was a known issue for a while. And people kind of talk about fixing it and so on. It got a bit more delayed than maybe the community would have expected, but then eventually there were some improvements. The version number 2 that came on this trying to add some randomization to the same algorithm. So the essence of the algorithm was the same, but they added kind of like a randomized prefix and suffix, and you could customize it with this Python hash seed. You could turn it off completely, or you could customize it to be something else. This kind of made it harder, so there weren't any register attacks or any, there weren't any register attacks, but theoretically the vulnerability was still there. So even though it was an improvement because it made it harder, it didn't completely solve the problem. Plus, it added a performance issue comparing to the first version. So eventually, we came to the last version, which we call zip hash. And zip hash was not an improvement of the first version or the second, but it was a completely new thing. And it's a family of pseudo-random functions that is optimized for short messages. And one of the nice things about, I can go and read this spec, which is what was proposed, and it's quite interesting. And one of the nice things was that it was as fast as version 1, but without the vulnerability, which is quite an ingenious solution, and it's quite intriguing. So if you want to see, these slides were done for Python UK on September last year. So actually, all these Python versions are not supported right now, or everything that is Python 2. But this is kind of the snapshot of some Python versions and where do they sit in terms of dictionary security. So if you have any version of Python 3, which probably you should, then you're using the most secure version of dictionaries we know of. So that is good news for you and for me and for everyone. So that is a bit of an overview of the security of Python dictionaries. And now we get to, And now we get to what I think is probably my favorite part of the talk, because it talks about how Python is built incrementally. It's not one genius idea, it's just a lot of very ingenious ideas built on top of each other. And there is a level of craftsmanship that goes into it that is amazing. This selection is completely personal, and you probably could have picked another selection of performance optimizations or other kinds of optimization, and they would be as awesome as this probably. But this is some example of fine-tuning that I find fantastic. So if dictionaries are going to be used everywhere, you will also care about performance in time, but you will also care about performance in space and how much space your dictionaries take. And this was an optimization presented by Raymond Hettinger that it's actually quite simple when you see it, but it took a while to come around. So imagine you have a dictionary. So this version over here was how it was before. So before we will have a very sparse table of your entries to your dictionary. So this is your dictionary basically. And this dictionary will always have a percentage of the table that was free. So if you start to add things to your dictionary, eventually it will resize to keep that percentage of free space. So eventually this was mostly unused space by design. So it wasn't just a snapshot in time, it was by design like this. But then Raymond Hettinger came and actually proposed this. So actually we could replace this sparse table with these two things. So on the one hand, we have an array, and a sparse array of indices. And then we have a compact table, which doesn't have any free space, with the actual entries. So for example, imagine I have my dictionary and I go and I add name first. So this is the first thing I'm gonna add, and I add it to my table. Then I'm gonna add age, and I add it to my table, you know, and it's kind of like, it's kind of the same information. You don't lose any information. And on top of that, if you maybe are paying attention on these indexes, you can see that now you remember also the order of insertion. So this is exactly the point in time where that depends on the poll we were seeing happens. Where these performance optimizations get added as a side effect, you get the insertion. So what are kind of the gains of having done this? Resizing becomes faster, iteration becomes faster. You get a lot of memory savings. There is a special optimization for small dictionaries. I don't remember the numbers, but it's quite significant. And then you also get that free side effect that now dictionaries remember the order of insertion. And this was only like behind the scenes change, so like nothing user facing or nothing you would notice, but it was quite significant. The second performance optimization I wanted to talk about, it was key sharing in dictionaries. So as we saw in the event poll, like behind the scenes, Python uses dictionaries for class instances, attributes. And this PEP allow sharing of that. I'm gonna give an example. So imagine you have this class, which is quite the same as before, like a person with a name, an age, and a salary. So basically, your attribute names can be put together inside the instance or can be stored separately. And if you have only one instance, it's kind of the same, really. But how do these escalate? So when you have two instances now, this is all shared information because they all have an attribute name, an attribute age, an attribute salary. So actually this, instead of being duplicated in each of the instances, it's separated. And this, if you have two instances, you only save one, but if you have thousands of instances, you start saving more. And this led to a memory improvement of up to 20%. So that was quite impressive. The optimization I want to talk about was string key optimization. So, you know, when you, kind of everything you do with dictionaries require you to compare keys, right? If you want to insert something, you compare to the keys you have. If you want to compare if the value stored inside the key is the same as something else, you also have to compare. So you have to do a lot of comparisons. Now, comparison of two random Python objects is something quite complex, actually, because you have to take the first object, fetch the undirect method, call it with this other object, check if it's define. This can raise an exception. If it's not defined, you have to fetch the undirect of the other object and call it with this one. And again, all this can raise an exception. So it's quite complex. But, and this is the beauty of Python, none of this can happen with strings. Comparison between strings is always defined. It will never raise an exception. It's quite quick. So this is what this optimization is about. Dictionaries with string keys are handled differently from all other dictionaries. And so basically, as we said, comparing two strings versus comparing two random Python objects is a lot faster and cannot raise exceptions. And why is this string key optimization so shocking or so vital? Is like most internal Python dictionaries benefit from it. So actually, even if we as user may want to use keys that are a bit more complex than just strings, like most of the internals of Python benefits from this implementation. And if you go look at the implementation for this optimization, it's actually just very simple. It's just an if. If the type of the attribute is of the key is a string, then so it's just an if. So it's probably like a less than 5 lines of code implementation or something like that. But the idea is quite impressive. And that was kind of my talk. So yeah, I'm a software engineer. I work at Tessian, if you want to check it out. And also I'm one of the colleagues of PyLadies London. So if you want to support or talk at PyLadies London, give us a shout. And that is my Twitter, where I tweet about Python and pictures of my cat. And these are all the references where I have taken most of this information. I think the PEPs are not here. Oh yes, the PEPs are here as well. So if you want, I can copy this list to the chat. And that was me. Thank you so much.
Thank you.
I'm going to stop sharing. Let me see.
Thank you, Gisela. We have a few questions. I'm actually going to answer the first one. Is from Vorn. Yes, we are recording this. We are not sure where we will share this, but there is recording going on right now. Then Gisela, we have a couple of questions.
Can I ask a follow-up on that? Gisela, will we be able to get a copy of your slides?
Yeah, sure, of course. Yeah.
Well, we can host them on djangolondon.com.
Let me, I can actually master that right now.
Okay, Gisela, we have a couple of questions from Ari. So
Okay,
I'm gonna read them. First is there is some code in it, so like probably if you open the Q&A panel, you will be able to read them. But first one,
I just opened the Q&A. So our Python version using CPH is still vulnerable to arbitrary key denial of service attacks. As far as we know, no. So the problems we know of were solved, unless someone can prove that this is vulnerable as well. To the best of our abilities, the answer is no. You mentioned the user-defined classes get done direct by default. I presume that is done direct under the hood by default is identity. So it's just checking against the identity. So you get something very limited. The identity default function.
Yeah, I think that's the same as the code sample Harry posted.
Okay, I haven't seen the codes.
Return self is other.
Yeah. Okay. Why does Python force you to redefine hash to keep hashability when you're like? Why doesn't it inherit the parents' hash?
Sorry,
Design, I think.
Can you read them out of laugh?
Yes, sorry. So if someone is asking why Python forces you to redefine dunder hash to keep hashability when you override dunderec, why doesn't it inherit the parents dunder hash? And that's a very good question. And I think that is design. I mean, I think it could have gone either way. My best guess was to avoid people from not being aware that this was the behavior they were getting.
Cool. I think that's all the questions. I just moved them all into the answered tab if anyone wants to check them.
Okay, while someone wants to wait for another question or give some time to someone, I'm gonna share the slide.